So we will continue with this particular part, that is principles of mathematical induction, which is an important chapter to prove the formulae. All type of formulas what we study for the grade 11, grade 12. Every time we use formulas, and every formula can be proved with the help of mathematical induction. So let us see the basics of this. If it is there in the review, I'll just go with that. That is a very, very basic one. Summary is there. Let Pn be the statement involving the natural number n such that P1 is true. So that P1 is true. And second, Pk plus 1 is true. Whenever Pk is true, then Pn is true for all n belongs to natural numbers. It's a very, very basic understanding of mathematical induction, that when Pn is a statement on the natural number n such that P1 is true. If P1 is true and Pk plus 1 is true, whenever Pk is true, then Pn is true for all n belongs to natural numbers. That is the very basic way of solving this questions. Okay, we just try for P1 and then we try for Pk, and Pk plus 1 is true, then obviously Pk is true. Like this we verify. You can see that a lot of different formulas are there, expansions are there in this. Now let us go for the complex numbers and quadratic. Complex numbers and quadratic equations, let us see how it goes. Okay, so we'll just see that. Okay, so review of facts and formulae we will do here. Review of facts and formulas are related to complex numbers. We will do review of facts and formulas of complex numbers. We will do. The first one is imaginary numbers. A given number is said to be imaginary if its square is negative. So root of -1, root of -2, and the root of -3, and the root of -4, etc. So we know that we do know what under root of square root, I will say square root of -1 by the Greek letter iota, transliterated as I. I to the power of 0 is 1, I to the power of 1 is I to the power of I to the I square is -1, I cube is -1, minus I. Why? Because I square, I is there, so I is root -1, and I square is -1. So I square, we know it is -1, and I, we know that is minus will multiply to that, and that's why we will be having minus I to the power of 4 is 1. Let n be the positive integer. On dividing n by 4, let m be the quotient and r be the remainder. Then n is equal to 4m plus r. I to the power of n is equal to I to the power of 4m plus r. And we can separate this I to the power of 4. So that is the thing. So we can separate this out. Under root of square root of -16. This written as obviously 4i and 3i. So square, we know it is -1, so -12 is the answer in this case. Complex numbers, the number of the form z is equal to a plus ib are called complex numbers where a comma b belongs to R. Here, a real z is a, imaginary z is b. Okay, that is real part of the value of z is a and imaginary part is b. If b is 0, then z is purely real, and a is 0, then z is purely imaginary. Z1 is a1 plus ib1, and z2 is a2 plus ib2. Then in this case z1 plus z2 is addition of both the real part, that is a1 plus a2 plus I b1 plus b2. Z1 minus z2 is equal to a1 minus a2 plus I b1 minus b2. Then we can say z1 into z2 is a1 a2, okay, minus b1 b2. So a1 a2 minus b1 b2 plus I a1 b2 and b and a2 b1. Conjugate of z, that is a plus I b is equal is z bar is equal to z bar a plus ib, a plus ib. The conjugate of z is equal to a plus ib, as z bar is equal to a plus ib bar, and it will be a minus ib. The modulus of z is a plus ib is you can say modulus of z is root of under root of a square plus b square, that we can have as the value. Modulus of z is equal to a plus ib is z bar is equal to a plus ib bar is equal to a minus ib. So that is a conjugate of z. Modulus of z, obviously we have to square both of the things here. That is modulus of z is equal to root of a square plus b square. Uh, that is the thing. Modulus of z. If you generally square it, so be very careful here. It is not the ib square. Don't get confused here. It should be root under root of a square plus b square. We are squaring only the values here of a and b, not the complete part. Okay. Why? Because I square, if you keep it, will be negative. So that's why you better understand like that. Z1 is A1 plus IB1 and Z2 is A2 is IB2. Then Z1 is equal to Z2. It means that real parts are equal and imaginary parts are equal. Now, if Z is A plus IB, then Z inverse is Z bar upon modulus of Z square. Whenever, so if I just write it here, this can be noted as Z inverse. Z inverse means 1 by Z, right? So Z is this much. So 1 by Z means it is A plus IB. If you go for the conjugate multiplication, it is A minus IB, and this is A plus minus IB. And square it, obviously after squaring A minus IB and A square, modulus is there. That's why you can say modulus of this is the root of a square plus b square. Be very careful here. Again, I'll tell you that there can be some confusion here. Modulus of z is square root of a square plus b square. So whatever is the value you're having, If it is a negative value, you have to take it there to the square, obviously. It will be in the positive part. Anyhow, the modulus will be a positive value. So that is the thing. And this will already square part. We can say, I'll just erase all of this. So yeah. So what is the point here is to be noted is if z is equal to a plus ib, then z inverse is z bar, that is z conjugate of z, upon modulus of z whole square, that is a square plus b square, and a minus ib in this form. And now it is distributive conjugate of z1 plus z2 is conjugate of z1 plus conjugate of z2. Uh, z1 minus z2 conjugate of that is again separated out in multiplication, again separated out in division, again separated, and again if we're adding to complex numbers where one is a conjugate, so in that case two real parts will be there, 2 into real of z will be there, and subtraction 2 imaginary will be there. Multiplication will lead to modulus of z whole square. So that is the part we have to understand. Z into z bar, that is the multiplication if you are doing, means the you can say values are a square minus it is a square plus b square form we will get is equal to the modulus of z whole square. So we are getting the same form. Okay, polar form if you see. So let us go for the polar part also. Polar part if you see of z is x plus iy is z is equal to r in bracket cos theta plus I sin theta, where r is under root of x square plus y square is equal to modulus of z and the value of theta, so that theta is greater than negative pi and less than equal to pi is called a principal argument or amplitude of z. When z is purely real, then it lies on the x-axis. If z lies in the positive side of the x-axis, then theta is equal to 0. Lies on negative side, theta is equal to pi. When z is purely imaginary, then it lies on the y-axis. Z lies on the y-axis above the x-axis, then theta is equal to pi by 2. Z lies on the y-axis and below the axis, then theta is equal to negative pi by 2. Z is equal to x plus I by a does not lie on any axis. When happens like that, then alpha, for which tan alpha is equal to imaginary of z on real part of z. When any complex number does not lie on any axis, in that case we have to find the value of alpha, then tan alpha is equal to imaginary part of z upon real part of z. Find the quadrant in which the p xy lies. Z lies in the first quadrant and theta is equal to alpha. Then argument of z is alpha, where it lies in the second quadrant, and theta is equal to pi minus alpha. Argument of z is pi minus alpha, that lies in third quadrant, and theta is equal to alpha minus pi, that is argument of z is alpha minus pi, and theta in fourth quadrant, theta is equal to minus alpha, and argument of z is minus alpha. In that case, fundamental proper theorem of algebra is a polynomial equation of degree n has at most n roots. That is a fundamental theorem of algebra. What is the fundamental theorem? We can just tightly say that a polynomial equation of degree n has at most n roots. The roots are at most n means if the roots are real, it will be intersecting with the x-axis obviously, and the equation is in x. And if the roots are imaginary, obviously it will be not intersecting, it will be in complex form. So that are the maximum part, means it can be lesser also. Now for this quadratic, we know that ABC belongs to real numbers and is not equal to 0. Alpha is minus b plus minus under root b square minus 4ac upon 2a, and b square minus 4ac is called a discriminant. When it is less than 0, the quadratic has complex roots. The root of a plus ib is equal to plus minus x plus iy, where x square is so under root of a plus ib is equal to a plus minus in bracket x plus iy, where x square is equal to half in bracket under root of e square plus b square plus a, and y square is equal to half in bracket under root of e square plus b square minus a. Simply by assuming root of e minus ib is plus minus x plus x minus iy, we may find uh, value of root of a minus ib in that case. Okay. So after this, we'll go with the linear equation one variable, maybe after some time. So yeah, this will go in the next session. We'll continue.